Assalamu alaikum. Today's plan is to cover two major topics of data structures. The first one is hashing, and the second one is priority queues. So let's start with hashing. So the concept of hashing actually involves a few building blocks. The first building block is the data structure itself. That is called a hash table. The second building block is called hash function. So hash function is just like an ordinary function, which essentially maps the keys and values. Uh, so by mapping, we mean that what kind of data element should be placed to which position of the hash table. So the hash function determines the position of a new element into the hash table. So let's start with a simplest possible example. So if you look at this table, this is the hash table. So this is the underlying data structure for this hash table is an array of size 10. So its indexes are starting from 0 going up till 9. And h of key is essentially the index. So h is the hash function. Key is the parameter which we pass to the hash function. And based on the key, the index is determined. So this process of determining the right index for a given key is primarily accomplished by the hash function. So in this example, we are defining the hash function as key mod size. So size is 10 in this example. So if our first element is 6, we pass this key 6 to the hash function. So 6 mod 10 is 6. So our first element goes at index 6. Then we pick the next element, we pass 81 to the hash function, and 81 goes to index 1 because 81 mod 10 is 1. We do the same thing for rest of the three elements. So 99 mod 10 is 9, 33 mod 10 is 3, and 55 mod 5 is 5. So far the things are like pretty decent. Uh, so if you look at these particular 5 elements, so each element is being inserted in a constant amount of time because the time is primarily dependent on the complexity of the hash function. And intentionally, we keep the hash function simple enough so that it can get things done quickly. So ideally, the complexity of hash function should be constant. It should not be dependent on the size of the hash table or the number of elements which are being inserted over here. So if you look at this example, size of the hash table is 10, which means that we have 10 places available in our data structure, which can possibly be assigned to different elements. But the number of elements or size of the input is 5. So we are inserting 5 elements to different positions in a hash table of size 10. And like one clue which you might get over here is that some spaces will remain unoccupied and they should remain unoccupied. We'll discuss these things as we go along in depth of hashing. So the only task which I wanted to emphasize at the moment is that because things have been designed in a decent fashion, so in this particular example, the complexity to add all of those individual elements is big O 1. So if I have to search an element, so for example, if I have to search 55, so we'll pass again 55 to the hash function. It will return us the possible index. We'll go at that index and we see if 55 is there, we'll be returning yes. Otherwise, we'll be returning false. So again, the search process is being done in big O 1 as far as this particular example is concerned. So you can take a pause over here and try to identify any issues with this scheme. You might have seen that if I try to insert some element like 53, so 53 is the key, we pass it to the hash function returns answer 3, but 3 is already occupied. So that causes a problem. So if I try to insert 53 in place of 33, then I'm going to lose one data item, or I might be refusing 53 to be inserted in the hash table. So such kind of situation where two keys try to get into the same index, this kind of situation is called collision. And that is one of the common problem which we might be facing while getting into any realistic or practical example of hashing. So our next subtopic is that how to resolve the collisions. We call those techniques as collision resolution techniques. And there are different possible standard techniques which are available to resolve the collisions or to handle the collisions or manage the collisions. And we can define our own customized collision resolution techniques as well. So let's go over them one by one. So we are starting with separate chaining. So if you look at this visualization, so on the left-hand side, we have the hash table. So separate chaining is a mechanism to resolve collisions in hashing, where inside the hash table, we do not store any data item. Instead, each index of the hash table serves as head of a linked list. So if you look at index 0, from here, a linked list is starting and going towards right, like 21, 14, 7, and so on. So this slash in this visualization represents that the next element is null. So there is a collection of different linked lists which are associated with this kind of hashing mechanism. So one major difference is that the hash table in itself is not containing the data itself. Instead, it contains references to the start points or starting nodes of different linked lists. So what happens is that in this particular case, size of the hash table is 7, indexing starting from 0 to 7. So if we have an element like 21, so 21 mod 7 is 0. So 21 should have been inserted over here if we have used the previously discussed hashing mechanism. But in this separate chaining mechanism, what we do is that we initiate a linked list from here and we insert 21 at start of the linked list. So same way, if we have 23, we take 23 mod 3, it takes us, we take 23 mod 7, it takes us to index 2, and we start a linked list over here. If there is 13, we take 13 mod 7, it is 6, we start the linked list from here. So now if you look at the structure of these linked lists, we have to somehow make sure that our insertion process is very efficient. And if we recall our basic concepts of linked list, which I'm sure you would have implemented by now, uh, we saw that how to add an element. So there are different possibilities. One possibility is that we add an element at the tail. The other possibility is that we add an element at the head. So if we are maintaining the tail pointers, we can get things done like in Big one at the end as well. But one safer option is that we always keep on adding a new element at the start of the linked list whenever there is a collision. So 21 was inserted. So if we know the tail, we can insert 14 because it also tries to hash to index 0. So we keep on extending that particular linked list. And in this way, our collisions are being managed and resolved, and we are not denying any new insertion in the hash table, but against every possible index. This index is called bucket. Against every possible bucket of the hash table, we are maintaining a linked list. So each array index maintains a linked list. Sorry. Collisions are resolved by appending keys to the linked list. Okay, so there is a term that this is efficient when the load factor is low. So we yet have to define this phenomena of load factor. So load factor is the characteristic of a hash table, which is notated as alpha, and it is ratio of n and m, where n is the number of keys, which essentially means that n is size of our data, and m is size of the array, which means that m is size of the data container, and n is size of the data itself. So ratio of n and m is called load factor. So if you recall our first example where we had 5 elements, so n was 5 and array size was 10. So 5 over 10 is half. So load factor is half for that particular example, which we saw at the start of the lecture. Okay, so given a hash table of size 11, and the hash function is that the key mod 11 is used to determine the right index. So our task is to insert these different items in the hash table using the mechanism of separate chaining. So this is the given list of elements which we have to insert in the hash table. So let's quickly draw the hash table first. So if you look over here, size of the hash table should be 11 because this hash function is determining that thing, and that is also given explicitly to us in the question. So our first task is that we draw a hash table of size 11. So we have index 0 over here, we have index 1 over here, we have index 2, we have index 3, we have index 4, we have index 5, 6, 7, 8, 9, and 10, and this makes it a hash table of size 11. So 22 mod 11 is 0. So what we do is that we start a linked list over here and we insert 22 over here as a node of the linked list. And 22 gets inserted over here, and its next is now available. At the moment, it is null, but it is available to point to any other node if someone else hashes to the same point. So 22 is done. Then we pick 5. So 5 mod 11 is 5. So we initiate a new linked list over here because there is no linked list here at index 5 at the moment. So element 5 is inserted over here and its next is null. So we pick 75. 75 mod 11 is 6 11s are 66. So it gives us 9. So we place 75 over here at index 9. And its next is also null at the moment. Pick 99. 99 mod 11 is 0. So now we already have a linked list at index 0. So what we do is that we just append the new element over here at index 0. So 99 lands over here. And its index is, sorry, its next is null. Next is 111. So 111 mod 10, mod 11. 11 tens are 110. So its remainder is 1. So 111 lands at index 1. Its next is null. The next element is 8. 8 mod 11 is 8. So it goes to index 8 and we place it here. And its next is null as well. Next and last element is 16. 16 mod 11 is 5. So 5 is an existing linked list. We just append this new element at the end of the linked list. So 16 goes over here. So if I've computed the mods correctly, I hope I have calculated them correctly and you can verify them. Then this will be the shape of the hash table after inserting all these elements. The first question is that what is the load factor of this particular hash table? So load factor is simply the ratio of number of actual data items. So load factor is n over m. So n in this case is, we need to count the elements. We have 7 elements. So 7 over 11 is the load factor of this particular hash table. Essentially, the number of nodes which have been inserted in the hash table are 7, and the total number of buckets are 11. So 7 over 11 is the hash table, is the load factor. What is the best case complexity to search an element? So just take a pause over here, try to identify yourself that what would be the best case scenario to search an element in this situation or in this particular example. So you might have come up with the idea that best case example is that if, for example, if I'm looking for something whose mod is 7 with 11, so if I land onto bucket number 7 that is empty, and I can decide in bigger one that that element is not there. So that's one kind of best case. The other best case could be that I'm looking for 22 and I land on index 0, and after one probe or after one step, I can decide that 22 is there in the linked list. What is the worst case complexity to search an element? So worst case would be that we land onto some index like 0 or 5, and we have to search the whole linked list till end. So for example, if I'm looking for 88, so which is not there, so 88 mod 11 is 0. So we have to like scan the whole linked list associated with the index 0, and after scanning that whole list, we'll be able to decide the absence of 88. And in that case, worst case complexity is actually size of the longest linked list. But what could be the worst case size of the longest list? That could be n itself, because if our hash function is poor, if we have not distributed the data in a decent fashion, we might have appended all items in one linked list. And that's the worst kind of design of hash table. So unlike most of the data structures which we have studied so far, there are certain things which are in your control as a programmer over here. And those things include choosing the right size of the hash table, choosing the right hash function, or designing the right hash function, such that you are able to scatter the data sufficiently and avoid collisions or minimize collisions. So the worst case complexity could be big N. And what is when n is proportional to m, when n is proportional to m, that means that when n is a function of m, like n is somewhat like some constant times m, then alpha itself becomes constant. And when what if m is very large? If m is very large, then that means that the hash table size is very large. That means that we are going to waste a lot of space, and alpha will be very small. But the positive side would be that we will be able to do things very quickly, but we'll be like doing that thing on the compromise of some memory waste. But what if m is very small? And in that case, alpha is no more constant. So we need to create a balance between very small and very large values of the size of the hash table. Okay, so that's what we call the kind of stuff which we have seen so far. That's what we call separate chaining. And now we are moving to another um, method of collision resolution that's called open addressing. Within open addressing, we'll be talking about three kinds of different sub techniques. The first one is called linear probing. So linear probing advocates that if a collision occurs, probe linearly. When we say probe linearly, that means that keep on moving to the next bucket and next bucket in a linear fashion until you find an empty slot. Uh, in quadratic probing, which is an alternate to linear probing, if a collision occurs, we have to probe quadratically to find an empty slot. And the third one, which we'll be discussing today, is double hashing. If a collision occurs, use another hash function to determine the probe step size. We will be doing and discussing all these three techniques in detail in a while. Let's start with linear probing. So in linear probing, let's go over this example. We have a hash table of size 7. So our initial state of the hash table is an empty hash table, somewhat very similar to given on the left side. We insert the first element, which is 76. It goes to index 6. Then we insert the second element, which is 93. It goes to index 2. When we insert the third element, it hashes to index 5. So 40 goes to hash 5. So far, there is no issue. When we try to insert 47, it tries to hash to index number 5. Now, this is critical to understand. When it tries to hash to index number 5, so 40 is already there at hash 5. So linear probing suggests that move to the next element. So we move to the next element, and that is already occupied by 76. So we try to move to the next element, and when we try to move to the next element, that means that we are incrementing one in the current index. So that gives us a new index 7, but that index is an invalid index, and that takes us out of the boundary of the hash table. So what we do is that we take its mod with 7, which is the hash table size, and this gives us 0. And this 0 takes us back to start of the hash table. So when we get here, so index 0 is available. So we insert 47 at index 0. So an extremely important point to note over here, and then there will be an exercise question in the coming slides, that 40, 76, and 47 are actually linearly co-located. They are neighbors of each other, because for next of 40 is 76, and next of 76 is now 47, and that is because of the circular fashion. Otherwise we'll be just like falling out of the hash table. So when we insert 10, we land onto index 3 because that's available. Then we try to insert 55. It hashes to 6, and 6 is already occupied. So when 6 is occupied, we do the similar kind of thing. We go to the next possible index, and over here next possible index will be 0, because 6 plus 1 is 7, and 7 mod 7 is 0. So that takes us to start of the hash table, but that is also occupied. When that's occupied, we go to the next possible place, and that gives us 55. And because that's available, so we just insert 55 over there, and that's how this mechanism of linear probing works. Okay, given a hash table of size 11 and the hash function h of key is key mod 11, we have to insert the following elements in the hash table using linear probing. So 22 mod 11 is 0, 5 mod, so let me try to label them. So I'm marking all those table elements with green, which are being inserted without any collision. So 22 is the first element. Our hash table is initially empty, so this is fine. There's no collision. 5 is the next element. There is no collision. 75 mod 11 is 9. Yeah, it's 9, so there is no collision. So when 99 comes in, 99 mod 11 is 0, and then there is a collision. So it tried to hash over here, but there was no space, and we are using linear probing. So we move to the next index, and then 99 gets adjusted at index number 1. Then we have 11. So 11 mod 11 is 0. So again, it lands to index 0. We move to the next element, which is 1, that's also occupied. We move to the further next element, and we hash it to 11 to index 2, and 11 goes over here. So then we go for 21. So 21 mod 11 is 10, and that gets hashed at index 10 without any collision. Our next element is 16, and 16 mod 11 is 5, but index 5 is already occupied. So we move to the next element, next bucket, and that's available, and 16 gets hashed to index 6. So this gives us the structure of the hash table after inserting all these elements using linear probing. So let's go over a quick exercise to strengthen our concepts of linear probing. So given a hash table of size 7, we have to insert these elements. And the notations are that the values given in the parentheses means that they are the values returned by the hash function. So those are the index numbers. So some hash function has returned these values, so we just use them. So the maximum index value over here is 6, smallest is 0, so we can safely create a hash table from 0 to 6, place all these values to their respective indexes, like Q goes to 6, W goes to 5, E goes to 0, R has to go to 6, but R actually collides with 6. So it tries to go to 0, and it collides with E, then it goes to 1. So R gets adjusted to position number 1, and then T tries to go to 5. It is not available. Then it tries to go to 6. That's not available. Then it tries to go to 0. That's also not available. Then it tries to go to 1, that's not available, and then it tries to go to 2, and that is available, and T gets inserted over there. So there were like a lot of number of hops or steps or probes to find the right place for T. So if we have to search for y, where hash value of y is 0, so how to locate 0? So how many probes are required to decide that y is not there? Take a pause, think, and answer your question to yourself that what will be the number of probes required to decide that y is actually not there in the hash table. So if you would have taken a pause, you might have come up to this conclusion that we first check index 0, which is the right index of y, but that's occupied by someone else. So there is a chance that if y is there, then it might have been placed somewhere else due to linear probing. So we go to the next bucket. That's already occupied by R. So we go to the next bucket. That's occupied by T. Go to the next bucket, which is index 3, and that is empty. And then we decide that y is not there, because if y would have been there, then it would have been placed just next to in the non-empty places, and which are like starting from 0 and going linearly in the forward way. So there's a concept of clusters, that how many clusters do we have, that how many groups of items do we have. So can you take a pause and guess that how many clusters do we have? If you would have taken a pause, we actually have one cluster, and the cluster is starting from here. And this cluster is not ending at 6, because 6 is naturally connected with 0. So this whole thing makes it one cluster, because we start from W, go to index 6, then go to index 0, then 1, 2, and so on. So all these items are placed in one cluster or one group. So if I have to insert a new item, if cluster size is very large, then there's a chance that I might be falling into a cluster. And the better strategy could be that if I somehow hash my elements in the hash table such that large clusters are avoided. When we say large clusters are avoided, that means that we are creating some empty spaces between the clusters, which are separators. And those give us a better probability to fall into an empty space. And that also results into smaller cluster sizes. So when cluster size is small, then the chances are that we'll be able to get out of the cluster very quickly as compared to a very large cluster. So for example, in the same example, if you look for some other element like x, whose hash is 5, then we'll have to essentially move through every element in the hash table to decide that x is not there, because it hashes to index 5 that is occupied by someone else. Then we go to index 6, which is also occupied by someone else. Then we go to index 0, and then 1, then 2. And then when we reach to 3, which is empty, then we decide that x is actually not there. So linear probing has a side effect, and that is what we call primary clustering. So by primary clustering, we mean that it in its nature, in its inherent property, it it intends to build continuous clusters. So whenever there's a collision, the next item is just next bucket, which is probed. Uh, and in order to overcome that thing, the second strategy which we are about to have a look at is called open address. In open addressing is called quadratic probing. So quadratic probing suggests that when we have of collision, we try to take jumps in a quadratic fashion. And by quadratic fashion, let's try to have a look at that. What do we mean by that thing? So our hash table is of the same size, which we just saw. We actually have the same input, which we saw last time. So let's try that how things are being hashed using quadratic probing over here. So our first element is 22, which gets hashed without any collision. So same case as that of linear probing. Then we pick 5. 5 gets hashed over here without any collision, no issue. 75 gets hashed to index 9, no issue. When we get 99, so 99 tries to get to index 1, index 0, but that is occupied. And what we do is that now the formula is that whenever there is a collision, so what we do is that we are running an iterative process. So h of key plus I is the step size, right? So h of key was our original answer. I is initially 0. So h of key plus 0 means that we try to insert it here, which did not work. Then we incremented I in our linear probing fashion. And if it works, we are fine. Otherwise, we'll keep on incrementing I. But in quadratic probing, what we do is that we increment it quadratically. So we do it h of k plus I square. I is starting from 0. So when I is 0, we tried this place for 99. It didn't work. Then we incremented I. So h of key plus 1 square is 0 plus 1, which is 99. And 99 gets inserted over here, and we are fine with this thing. Now, when we get to 11, now things become, so far things have been very similar to what we saw in linear probing example. Now, for 11, things are going to become different. And let me try to change the color to make it more prominent. So when we pick 11, it hashes to index 0. Why it hashes to index 0? Because h of k plus 0 square is h of k, which means we are talking about index 0, and it didn't work. So as it didn't work, so what we do is that we increment I, and we go for the next I that becomes 1. So 1 square is 1, so that's why it is behaving in the same way as that of the linear probing, but that's occupied by 99, so that also does not work. Then we increment I, and over here it makes the difference, and that is that we make this 2. So h of key was 0. 0 plus 2 square is 4, which means now as we have seen the pattern that things are like getting into one cluster, so we try to increase our jump size quadratically. And that means that we have to skip some spaces in between, and this quadratic relationship is going to help us that way. So 0 plus 4 is 4, and we land on into index 4 rather than like moving in a continuous linear fashion. So element 11 gets hashed to index 4, and that's how quadratic probing is different than linear probing. Now if you look at the reason, or like the key that it is more attractive to us than linear probing, is that it is breaking the clusters. When it breaks the clusters, that means that same number of data items are getting hashed to more number of clusters, resulting into smaller clusters. And smaller clusters are attractive to us because if we get stuck into a cluster, we'll be able to get out of the clusters very quickly and make a decision about the presence or absence of a particular element we are looking for in the hash table. 21 mod 11 is 10, that gets hashed conveniently because there's no collision. Let's now focus on the last element. Let me clean the screen a little bit. So now our next element is 16. 21 is gone. So we are now focusing on 16. 16 mod 5 is 16 mod 11 is 5. So it tries to get at index 5, which is not available. So what we do is that we do h of key, which is h of 16 plus 1 square, because I was initially zeros. Now we try 1 square, and that gives us this index, and that's available. So 16 gets hashed over here. Just imagine that if it would have been already occupied by someone else, then what we would have done, then we would have trashed this function. We would have incremented I, and we would have gone to h of 16 plus 2 square, and that would have given us 5 plus 4, 9, and that's already occupied. If that is occupied, then what we do is that we make it 3 square, and when we try to get out of the boundary of the hash table size, then we have to always take mod with the hash table size, so that we can uh, limit our answers within the valid range of indexes. So this is all about quadratic probing. Quick exercise to strengthen our concepts of quadratic probing. We have been given a hash table of size 7, and the numbers given in the parentheses are the indexes given by our hash table hash function. So Q goes to 6, W goes to 5, E goes to 0. So there's no issue for the first three elements. So when we get R, so R tries to hash to index 6, which is not available. So because we are into quadratic probing, so what we do is that we say that H of R plus 1 square is tried, and we take mod of 7 with the overall answer. So this is 5. So sorry, H of R is 6 plus 1 square is 7. So 7 mod 7 is 0. So we try to get here, but that's also occupied. So what we do is that we then try 6 plus 2 square. So that gives us 6 plus 4, which is 10. 10 mod 7 is 3. And then 3 is the place where we insert R. So if we have to search for Y, whose index is 0, how many probes are required to decide? Take a pause and try to figure out that how many probes or comparisons are required to answer that Y is not there. We did the same thing for linear probing as well, but now our hash table structure is different to quadratic probing. And for the search process, we should also be using the same quadratic probing strategy to locate Y. So what we do is that we hash Y. The first index where we land is 0. So that is not occupied, that is occupied by someone else. That's not Y. So we move to one, this hash function plus 1 square, and that's empty. So we can, after one probe, after two probes, we can decide that Y is not there. The first probe was at index 0, the second is index 1, and that's empty. If Y would have been there, Y should have been at index 1. So we decide quite efficiently as compared to linear probing. So the second question is that how many clusters can you see over here in this example? Now pause the video and try to answer it yourself. So if you have paused it, and you might have figured it out. So there are like two clusters. One cluster is of TR. Other cluster is starting from here that includes E because of the circular relationship. And these are the two clusters which we have over here. Okay, our last strategy of resolving the collisions is called double hashing. So hash function is used to compute the bucket numbers. That's what we know. If available, then insert the element. If not available, then use secondary hash function to compute the jump size. So in linear probing and quadratic probing, we have been using this kind of thing to compute the jump size, but that thing was either linear or quadratic. So in linear probing, that was just simply we were adding I into the hash table size, and that was helping us to move I jumps forward from the current answer to make it linear probing. And for quadratic probing, we were adding I square to compute the the right index after adding that jump size. So over here, the secondary hash function is again in the control of the programmer. You can define another hash function which will contribute in assessing the next location if you end up into a collision. So from the programming perspective, this gives you more freedom to decide the mechanism of hashing things if you know the nature of your data or distribution of your data. And at the end of that whole computation, you have to wrap around at the end of the hash table to avoid any out of index exception. So how good or bad is the idea of double hashing? This is primarily dependent on the quality of your hash functions. So you might be like designing some messy kind of hash functions which end up into a lot of collisions as compared to previous collision resolution strategies, or you might be really coming up with some efficient mechanisms to resolve the collisions. And as we succeed to resolve the collisions quickly, we are actually enhancing our insert and search complexities. Let's go over an example. So this time we have two numbers given with every object. So first number is the answer of the primary hash function, which we have to use in any case. Second one is being returned by the secondary hash function, and that's what we'll be using for resolving the collisions if we end up into that kind of thing. So if you look at Q, its first answer is 0. So we just inserted Q and we don't use the value returned by secondary hash function because that is only applicable when there is a collision. So for W, we go to index 4 and that is the only thing which we use. We don't use 3 for that. For E, our what we have is that we are is trying to get over here at index 0, but we have a collision. Now we can use this thing too. So what we do is that we are essentially doing this kind of formulation that h of key plus I times I is the attempt number, which is starting from 0. I times h2, so I should have called it h1 of key, which is the first, which is the answer returned by the first hash function, and then h2 of key is the answer returned by the secondary hash function. So when we are using, when I is starting from 0, so this whole thing becomes 0, and that means that we are only using the first value in the first attempt. If it fails, I is incremented, that means that I is 1. So we simply add those two values, 0 plus 2 is 2, so E goes to 2. If that would have been a collision again, then I will be incremented, and then we'll be multiplying the answer returned by the secondary hash function with 2, add it into h1, and wrap it around to limit the uh, possible indexes, and then find the place. And we'll keep on doing this until the collision is resolved. So R tries to go to 2, but that is occupied. So what we do is that 2 plus 3 is 5, so R goes over here. For T, we try to go to 4, but that is occupied. So what we do is that we do 4 plus 2, which is also occupied. So when it is occupied, then we increase I, and that means that we are now doing 4 plus 2 times 2, and then we wrap it around. So 4 plus 2 times 2 is 4, that is 8. 8 mod 7 is, okay, what did we do? Something, so 4 plus 2 times 2 is 4, this is 8. 8 mod 7 is 1. Sorry, I think I missed this point that T is being inserted. So T tried to get inserted over here when we did 4 plus 2. So this place was empty and T got over there, right? So this T is actually this T. So we won't be going to this step. Sorry for that. Okay, so search for Y. Take a pause and figure out that how many probes are required to decide Y, whose primary hash function is returning 0 and secondary hash function is returning 3. So primary hash function gives us 0, so we try to locate Y at index 0, which is occupied by someone else. So we do 0 plus 3. So 0 plus 3 is available. So in two probes, we decide that Y is not there. How many clusters are there? Again, it has two clusters. One is the cluster which is made only by E, and the second cluster is this one, which includes this part, somewhat very similar to what we saw in our previous examples. All right. So given a hash table of size 13 and following hash table, insert these elements using these two hash functions, I would strongly suggest that take it as the homework, do it yourself. Slides will be available to you, and solve this answer yourself. If you face any difficulty, then let us know. So don't look at the answer before solving it. What is the probability that a new element to be inserted in the hash table will end up in a collision in the first attempt? That is primarily determined by that how many elements are there in the hash table and what is the overall space of the hash table. So load factor determines the probability that the new element to be inserted will end up into the collision. So at the start, n is 0, so alpha is 0. So there's 0 probability that you will end up into a collision at the start. But as you keep on inserting more elements, this probability will start increasing gradually. It depends on the actual values of n and m. So if m is reasonably large, then this probability will remain in control. What is the probability that a new element to be inserted in the hash function in the hash table will not end up into a collision is 1 minus alpha. So if alpha is 0 at the start, 1 minus 0 is 1. So we have 100% probability that we won't be having any collision. So how many trials will be required on average before the success? There is 1 over 1 minus alpha. Practically, hashing is an efficient choice if alpha is not close to 100. So if you play around with different substitutions of alpha over here in this expression of average number of trials, you'll be having a very good clue that how load factor plays a critical role in determining the average number of trials uh, or average number of probes which you need to perform in order to look at a particular element in the hash table. Okay, the last thing in hashing is the phenomena of rehashing. So sometimes you keep on inserting elements into hash table and n grows significantly. So then we might be hitting an extreme condition where alpha has increased significantly, which means that load factor is now getting closer to 1. And that might be a time for you as a manager of your hash table or database administrator that you might be doing some maintenance of your data. And so rehashing is essentially a maintenance activity of the hash table. And that is that change the size of the hash table, adopt the hash function with respect to the new size, and rehash or recalculate the indexes for all elements and insert them from scratch in the new hash table. But this is not a like frequent activity. This is the kind of activity which happens at the back end to optimize the performance of your hash table. So this is sometimes we call it an offline activity. So that's it as far as hashing is concerned. So you will be getting an assignment on implementing some concepts of hashing this week. So keep an eye on our discussion forums and your Moodle to have a clue that when the assignment is there, right? So our next topic for today is, you can take a pause, but because I'm recording it, so I'm moving forward. Uh, our next topic for today is called priority queues. Okay, so let's very quickly recall our basic concept of queue. Queue is a data structure which follows the first in, first out protocol. So arrival time in the queue matters. The item which came first will be given higher priority. And dequeue operation is based on the sorting of arrival times. So priority queue is essentially a queue which has an explicit additional attribute of priority, and that priority matters. So dequeue operation is based on the sorting of priorities. So the element which has the highest priority will be dequeued first, irrespective of that when that element was inserted. And queue operations stores priority of each element. So dequeue operation is based on the highest priority. So there are different mechanisms to implement priority queues. So one very simple mechanism of implementing a priority queue is sorted sequence. So sorted sequence is essentially a sorted array. So in queue operation is essentially inserting a new element into a sorted sequence such that that sorting the mechanism remains in place. So for example, if you have to insert these elements A, B, C, D, E, and F with the given priorities which have been given in parentheses, so then A is inserted first. Then when we have to insert B, then that B goes before A. When we have to insert C, that goes before C, because we are essentially maintaining the order of priorities. So once we are done with all insertions, so the element with the highest priority will be at the end. Okay. So f of 6 is the element which has the highest priority, that will be at the end, and then the element with the lowest priority will be at the start. So can you guess that what has been the complexity to insert a new element in a sorted sequence? That is big of n, because we might have to shift all operations, all elements one step towards right, and that takes us to big O n. What is the element to dequeue any element? So dequeuing from this kind of priority queue where we are using a sorted sequence at the end is now easy, because we know that the element with the highest priority is at the end, and we just simply land onto the last element directly because this is an array, and then we dequeue that element. So our dequeue operation will be the element, will delete the element which has the highest priority, and that will be deleted in big O of 1. The alternate mechanism to implement priority queues is unsorted sequence, where we keep on inserting elements without sorting them based on the priorities. But when we have to delete an element from the data structure, then we need to take care of that thing. So for example, if you look at this, the same example, so we can insert them in the same order as they're coming. So A is the first element being inserted, goes to index 0, then B, then C, and we are not doing any shuffling or shifting during that whole process. But who is the element which has to be dequeued first? That is the element which has the highest priority. And where is that element? That's what we don't know, because we had inserted them in the array without looking at their priorities. So we need to find that element which has the highest priority first, and then we'll be able to delete the element. So what will be the complexity to enqueue an element? Yes, it's constant because we are not really making any comparisons. We are adding new element towards end of the array. And which element has to be dequeued first? In this case, that is F, but we need to, before we decide F, we need to walk through the whole data structure and decide that that element is F. After making all those comparisons, we'll be able to decide that F is the element which needs to be dequeued, and its complexity is going to be big O n. So in order to implement priority queue, we have another special mechanism, which is a better alternate as compared to sorted and unsorted sequences, that is called heap. So heap is a complete binary tree. So if you recall your basic concept of complete binary tree is a binary tree which is filled at all possible levels except the last level, and the last level is filled from left to right. So heap is a complete binary tree which follows heap order property. And heap order property is defined as that for each internal node, its priority is greater than that of its children, which means for each non-leaf node, its priority or its key is greater than that of its children. And then there is no discrimination between children. Left and right child might be having any kind of relationship that is okay for heap, which is different than what we saw in the case of binary search trees. Uh, so this is the variation which is called max heap, which means the priority of the parent is greater than both of its children. And the other variation is called min heap, where the priority of the parent is smaller than that of its children. So that's just a matter of implementation, just like we implement sorting in ascending or descending order. So that does not really change the basic concept. So if you look at this tree, so this is an example of heap. So let's check two properties. The first property is that is it a complete binary tree? Yes, it's complete binary tree because it is filled at all possible levels except the last level, and the last level is filled from left to right. So property number one is fine, it's a complete binary tree. The second property is the heap order property, and we need to verify that does it fulfill the heap order property, and that is that for each non-leaf node, is it greater than both of its children? So 16 is greater than both of its children, 14 is greater than both of its children, 10 is greater than both of its children, 9 is greater than both of its children, and 11 is greater than both of its children. Rest of the nodes are leaf nodes, so that heap order property does not apply to the leaf nodes because they don't have the child nodes. Okay. So let's build a max heap. Uh, so we've been given these elements in this order, and our task is to build the heap. So let me try to use this white space to build the heap. So we start with 4. We start with 8, which is the first element. So because our tree, our binary search tree is empty at this stage, so 8 becomes the root node. and it's a complete binary tree of size 1. Then we pick 4. First, we insert it into the complete binary tree, and that says that if that the previous level does not have space, which it does not have, we move to the next level and we start filling it from left to right. So as we insert over here, our next task is to compare it with its parent. So if it is smaller than its parent, then that's fine. If it is not smaller than its parent, we can swap them. So 4 is fine. So our next element is 10. So we just insert it at this place because our first step is to make sure that this remains a complete binary tree. And the next step is that we try to verify whether 10 is okay with its parent. And in this case, you can see that it's not okay with its parent because this is greater than its parent. So we get them swapped. So 8 gets swapped with 10. Then we insert 2. So 2 goes on, 2 cannot be inserted on the previous level. That is completely filled. So we start a new level and 2 goes on the leftmost position. So we compare 2 with 4. That is fine. That does not violate the heap order property. The next element is 14. And 14 gets inserted onto the next possible place in the complete binary tree. We compare 14 with 4. That is not okay with its parents. So what we do is that we swap them. 4 comes here, 14 goes here. Then we compare 14 with its parent, and 14 and 10 are not okay. So 14 goes here on top, becomes the root node, and 10 replaces 14. So now this is the complete, this is the heap. Now, another important thing which you must have noticed, and let's talk about that explicitly, that whenever there is a violation of the heap order property, we are moving from leaf to the root. And the maximum number of swap operations are same as length of that branch. Because it's a complete binary tree, so we know from our basic concepts of complete binary tree that height of the complete binary tree is log n. So maximum number of swap operations are going to be log n operations, and each operation takes constant time. So essentially our total complexity of inserting a new element is intuitively log n. So I would strongly suggest that take a pause over here and insert rest of the elements on your own. And if you have done them, then let's quickly insert them just to complete the solution. So 14 goes on left of 8 over here. Sorry, 40, it's not 14, it's 19, which goes over here. 14 has already been inserted. So 19 is compared with this parent, that's not fine. So we swap 8 and 19. Then we compare 19 with 14, that's not fine. So 19 goes on top. Again, log n operations, which are same as height of the complete binary tree. We pick the next element, which is 20. So 20 goes on right of 14. We compare 20 with 14, they are not okay, so they get swapped. 14 comes here, 20 goes here. Then 20 is compared with 19, they're not fine, they get swapped. So 19 goes here and 20 becomes the root. So this is the heap. The next element is 13. We can't insert 13 on the same level where we have been inserting so far. So we start the new level. 13 is inserted at the leftmost position of the new level. So 13 and 2 are not fine. So we just swap them. So 2 goes down, 13 goes on top. 13 and 10 are not fine, they get swapped. So 10 goes here and 13 goes here. Then we insert 13 and 20 are fine, so we stop here. So then we insert 15. 15 goes on right of 10. Again, they are not fine, so 10 comes here. 15 goes in place of 10. 15 and 13 are compared, they are not fine, so 13 comes here. 15 goes in place of 13. And 15 and 20 are fine. So 15 is done. 7 is inserted on left of 4. So 7 and 4 are not fine, so they get swapped. 7 and 15 are fine, so we stop our swapping process over here. So 7 is settled. The next element is 11. So we try to insert 11 on right of 7. And we see that they are not fine because 11 is greater than its parent. So 7 comes down and 11 goes up. and 11 and 15 are fine, so we're done. So if I try to draw this whole thing like in a relatively neater fashion, so 20 is the root node, 19 is the right child, 15 is the left child, 13 is the left child, 11 is the right child of 15, 8 is the left child of 19, 14 is the left right child of 14, 14 is the right child of 19, 13 has the left child, which is 2, its right child is 10, and left child of 11 is 4, right child of 11 is 7, and this makes it a complete binary tree as well as heap. Now, before we move forward, let's have a look on another important characterization of what we have seen so far. And that's an interesting perspective that should help you for implementing heaps in your last assignment as well. Okay, so if I try to treat this whole thing as an array, so we know that indexing in the array starts from 0, goes up to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So there are total 11 elements. So this is the last index. So we can do a similar kind of indexing mechanism on this tree, and that means that we can use arrays to implement these kind of trees. So this, if this is index 0, this is index 1, this is index 2, this is index 3, this is index 4, this is index 5, this is index 6, this is index 7, this is index 8, this is index 9, and this is index 10. So given those elements in that order, final shape or placements of those elements should be in this kind of fashion if they are being stored in an array. So array is like one interesting choice and relatively easier choice to implement heap. And you'll be expected to use arrays at the back end while implementing heaps in your assignment. So now the last interesting thing which I would like to discuss in this part is that what is the relationship of indexes between children and the parents. So take a pause over here, try to figure out that if who is going to be the left child of a node whose index is I, left child of index I, how would you figure it out? So that is the question. And once you're done, then try to figure out that how you will formulate the index of right child of some index I. And you can do it using your basic intuition and this visualization. So that's one of the major purposes of this visualization that we did it here on the screen in steps. So take a pause, try to figure it out. So if you've taken a pause, you might have already landed onto this thing that if index is, if I is 0, then 1 is the left child, which means, and right 2 is the right child. So if I is 4, 9 is the right child. So the relationship, the kind of relationship which which we have been able to figure out is that there is 2i plus 1 is the left child. So if we know the index of the parent, we can use this expression 2i plus 1 and we can compute the index of its left child. And same way, we can use this expression to find the index of the right child, that is 2i plus 2. Right? So you can intuitively as well as empirically verify it using this visualization and convince yourself before you move forward. And that will really help you in your implementation because we are like computing the indexes of left and right children using the index of the parent. So that is essentially going to help us in the in this whole this implementation stuff because if you know the index, we can directly jump in big O1 to that particular index. Okay, so this will be the resulting tree which we have already drawn. So type complexity to insert an element is log n, because in big O1 we insert the element at the next possible index in the array, and then we use that property to build the heap. We call it heapify up. So the maximum number of steps to ascertain the heap is log n. So the total complexity is log n to insert a new element. So what if we have to dequeue an element from the heap? Who has to decide the element to be dequeued? That is given, that is for granted. And because it's a priority queue, the element with the highest priority has to be dequeued. So who is the element which has to be dequeued? That is always the root. So there's no other choice, because this is a priority queue and the element with the highest priority is going to stay on the root. So that is the item which has to be dequeued. So if you like, well, let's go back to that visualization, which the kind of tree which we had come up with. So let's try to dequeue 20. So what will happen? The first step in order to dequeue 20 from here is that we locate the last element. We swap these two elements. So 7 goes here on top, 20 comes here. As 20 comes over here, we disconnect 20 from the tree. So size of the tree has been decreased by 1, and essentially that is the last element which we have we have cut from the tree. But 7 is so complete binary tree thing is in place with the reduced item, but 7 might not be at its right place. So 7 is compared with both of its children, and it gets swapped with the larger child. So 19 takes the top space and 7 comes down. So we're doing somewhat like the opposite process of insertion. So 7 is then further compared with both of its children, and it gets swapped with the larger child. So, and 7 gets settled over here. So the maximum number of steps required to do this whole thing are from top to, from root to leaf. And that is again log n because of that complete binary tree property. So after deleting one element, which was 20, this will be shape of the tree. So if we try to delete one more element, then again, the element is for granted that is 19. So in order to delete 19 from here, but the first thing we should do is that we swap 19 with the last element, and the last element is 4 this time. So 19 goes here, 4 goes on top, and then we disconnect 19 from the tree. So our remaining part is now this tree, which has one lesser node, and 4 is on top. So complete binary tree property is in place, but heap order property has yet to be verified. So 4 gets compared with both of its children, which are 15 and 14. So 4 gets swapped with the larger child. So 15 goes on top, 4 comes down. Sorry. So 4 comes down, and then 4 is further compared with both of its children. 13 goes up, 4 further comes down. It is compared with both of its children again. 10 goes up, and 4 comes down. And this is the resultant heap after deleting two elements one by one. So each deletion is taking log n time. So the time complexity for deletion is also log n. So take it as homework. This array has been given. Try to draw the underlying complete binary tree to check whether it's a heap. So first way to check whether it's a heap is to do it intuitively and through visualization. So draw the tree, figure it out if it's a heap. Once done, so take a pause over here. Once you're done, then design an efficient algorithm on your own to check if the input is heap. And we are making a big assumption over here that underlying structure is an array. So we have to maintain that heap order property in the array. So I'm asking you to implement this as your homework, but we'll be using this implementation as part of your last assignment as well. So if you start it on time, that will be really helpful for your final assignment, which will be released next week. So what is the complexity of your algorithm? Try to figure it out. Okay. So is it a heap if we consider elements from the index, from the start to index number 12? Again, homework. Is it a heap if you consider elements from start to index 13? Yes or no? Okay. If not, how to make it a heap? Again, try to implement it. what will be complexity of your algorithm, and we are done with heap. So in our next session, next week, we'll be using heaps to do some other amazing stuff. Thank you very much.